Hello everyone, today we'll be presenting our project Voice Controlled LED System using Support Vector Machine and MFCCs. The core idea is to recognize simple voice commands like on, off, 1, 2, and 3 and use them to control an LED in real time. This project directly connects to signals, networks, and systems because it treats your voice as an input signal, processes it through multiple signal stages, and finally produces a controlled output, the LED lighting up in different colors. In this system, the voice acts as the analog signal, which is then sampled, filtered, transformed, and classified using a combination of signal processing and machine learning techniques. We use Python libraries like Librosa for feature extraction, NumPy for signal operations, and scikit-learn for the SVM classifier. So essentially, we are applying theoretical SNS concepts like signal acquisition, transformation, and system response in a real working application. When we speak into the microphone, our voice is captured as a continuous time analog signal. To process it in Python, we first sample the signal at 22,050 Hz. This converts it into a discrete time signal that digital systems can handle. Next comes pre processing. This is where we clean and prepare the signal. The first step is voice activity detection, which checks if the input actually contains speech or silence. We do this using the root mean square energy of the waveform. RMS measures the average energy level, and if it's below a threshold, we ignore the signal as noise or silence. We also apply a trimming function to remove silent parts at the beginning and end, improving the clarity of our data. This stage is crucial as it ensures that only meaningful parts of the signal are analyzed later. In SNS terms, this pre processing stage acts as the front end filter network, eliminating unwanted low energy signals and improving the signal to noise ratio before further analysis. Once the audio is captured, we need to extract features that represent its important characteristics. Here, we use MFCC, Mel-Frequency Cepstral Coefficients, one of the most powerful speech features in signal processing. MFCC works by first converting the signal from the time domain to the frequency domain using the fast Fourier transform. Then, a set of Mel scale filter banks are applied. These act like a network of bandpass filters that model how the human ear perceives sound frequencies. This is directly related to the frequency response and filter design concepts studied in SNS. After that, we take the logarithm of the filter outputs to simulate human loudness perception and then apply the discrete cosine transform to obtain the MFCC coefficients. Finally, from these MFCCs, we calculate statistical features like mean, standard deviation, minimum, and maximum, which describe the overall spectral behavior of the voice signal. This entire process converts our raw sound into a compact numerical vector, effectively the system response of the speech signal. After extracting the MFCC features, the next step is to train a support vector machine to recognize patterns in those features. The SVM acts like a nonlinear system that separates input feature spaces into distinct output regions. Here, each region represents a command on, off, 1, 2, or 3. We use the RBF, that is radial basis function kernel, which transforms our input data into a higher dimensional space, allowing the model to handle nonlinear relationships. In SNS terms, you can think of this as applying a nonlinear transformation system that enhances separability, with very similar to how we model nonlinear networks in system theory. Before training, we also normalize our features using a standard scaler, ensuring every input signal has zero mean and unit variance. This standardization step helps the system stay balanced, much like stabilizing gain in a control system. Finally, we validate the model with cross validation and measure accuracy and confidence, which indicate the reliability of our system output. In real time, the system operates through a clear signal flow network. The microphone captures the analog input, it's digitized, pre processed, converted to MFCC features, classified using SVM, and finally, an LED output is triggered. Each of these stages can be viewed as a subsystem. Together, they form a complete signal processing chain similar to cascaded systems studied in SNS. The response time between speaking and LED activation represents the system's delay and latency, which are important parameters for evaluating real time performance. This project achieves an average inference time of less than 1 second, showing that our system is both fast and stable. Essentially, this slide connects theory of application. It shows how discrete time systems, signal pathways, and cascaded blocks interact to form a responsive network. The LED visualization acts as the system's observable output. Each recognized command corresponds to a specific color: yellow for on, gray for off, red for 1, blue for 2, and green for 3. This visual feedback represents the system's state response to a given input signal. The system instantly updates when a new command is recognized, just like a feedback control loop in an electrical network. We also display the recognized command, confidence level, and response time on the screen using matplotlib. This provides both visual and quantitative evaluation of the system's behavior. In SNS terms, this demonstrates how a discrete time input signal leads to a measurable, observable output, verifying the entire input output relationship of the system. In conclusion, this project successfully connects signal theory, system modeling, and machine learning into one integrated setup. It demonstrates how speech, a complex analog signal, can be analyzed, modeled, and controlled using digital systems. Through this work, we applied several key SNS concepts such as signal representation, filtering, transformation, feature extraction, and system response analysis. In real time, the system recognizes multiple commands with high accuracy and minimal delay, showing both stability and responsiveness. For future scope, we can enhance this by using deep learning models, improving noise robustness, or deploying it on embedded hardware like Raspberry Pi for IoT control. This paves the way for intelligent voice activated systems combining the power of signal processing and modern AI.
On, off, on, 2,
1,
3,